original Mars helicopter, where'd you go? Oh, yeah. The original Mars helicopter idea, you were going to use a Samsung cell phone architecture of some sort.
Yes,
Qualcomm, whatever. Most drones on Earth use GPS navigation coupled with a magnetometer. Now, you don't have GPS on Mars. Are you going to keep the magnetometer on board?
It's probably there, but I don't know what's on the chipset.
Please keep it.
We have very high powered magnets powering our rotors, which are just close proximity. It's not on the
Well, actually, we've checked some of those motors, and the flux on the rare earth magnets are so closely coupled, just a few centimeters away, you get perfect signals. Mind you, we tried to get a magnetometer in Mars 2020 and on Curiosity and failed on both rounds, even though we had $3 million matching from private sources. Anyway. That's an aside, but as you may gather, I am a magnetist. I study magnetism, I live and breathe it. I'm also a biologist, and as mentioned in the kind introduction, I am fascinated by small magnetic objects and things. One of my lab projects at the moment is unraveling the biophysics of the magnetic sense organs in animals, which actually I think may have evolved on Mars initially. So we'll make that straight. So what I would like to focus on in the brief 25 minutes I have today is whether the terrestrial biosphere could have started on the flanks of Tharsis. And this is kind of a nutty idea, but not so nutty when you think about it. The real title, an analysis of the electrochemical environment of early Martian high-altitude glaciers during late Noachian time. And the reason this is important is that we know Mars has been throwing rocks at us for 4.5 billion years. We have on the order of 200 Martian meteorites. Some of them, using magnetic studies as well as argon studies, we know got here in low temperature trajectories. They're not heated. So phrasing it in a little different way, Mars has been spitting at Earth for 4 billion years. That has implications for planetary protection as well. On the other hand, if you realize that, and you say, well, if Mars ever did evolve life, if life somehow had either gotten to Mars or evolved there, the natural transport mechanisms are there. Those Martian meteorites get to Earth without heating. And so the problem of the origin of life cannot be divorced from Mars. If it had evolved on Mars, it would be here, it would be us, and we might not know it. We probably wouldn't know it. So that actually makes an interesting prediction in terms of the environment of Mars. But when you step back from that a little bit more, and you say, well, compare Earth and Mars, which I'm going to be doing here very quickly, why might Mars have been a better place? And there's a very simple, and I think a very powerful argument, when you look at the early environment of Earth and Mars, that argues Mars might have been a better place. And it comes down to electrochemistry. So very quickly, Earth and Mars, life is here now, no visible life on Mars. There's a deep gravity well on Earth. It makes it very difficult for meteorites to get ejected from Earth. We have tektites, they're molten materials, but we don't have any ammonites with fusion crusts showing they were ejected and they came back. We have 200-odd Martian meteorites. It's easy to get off of Mars with an impact. We have a horrible rock record actually on Earth of the time where we think life evolved. It's been buried, it's been burned. On Mars, it's there, it's excellent. That time interval where we think life evolved somewhere is preserved on Mars. So here's really what I'm going to tell you. Electrochemically mean I'm wearing a biological hat as well as a geological hat. Was the original metabolism on Mars, not of Mars, but of life, sloppy or precise? And if you look at the scenarios for the origin of life, particularly where people think Mars may have, or life may have evolved in a weird, restricted, extreme environment, I raise my hand and say, if you look at what lives in those extreme environments on Earth, they didn't evolve there, they moved there. The way natural selection works, Darwinian evolution, is you take a sloppy system and you make it better. If you apply that reasoning to the fundamental metabolism that drives all life and all cells, you want an ancestor that starts in a very sloppy, energy-rich environment. So my focus on life, don't look at Europa, don't look at Enceladus. The electrochemistry there is minimal. Look for a place where we have a wide chemical variability. And I found a place. It's on Mars. It's the Tharsis province. And in fact, looking at that environment 4 billion years ago, 4.5 billion years ago, solves a hell of a lot of the problems we have trying to figure out how life evolved. So I'm going to focus on Tharsis. I'm going to worry about ozone in the atmosphere. Very elegant studies by geochemical groups in San Diego. And then where it might be. So here we go. Bear with me. This is a science talk. So life is driven by oxidation and reduction reactions, and if you can see my little pointer moving around here, if you have a half reaction here that dumps an electron this way, you gain energy. If you go the other way, you lose energy. So all metabolism on Earth drives this way. So when you look at those coupled reactions and look at the biochemistry, you find that there are electron transport processes that sit and dump electrons from highly reducing to highly oxidizing. And each little step generates enough energy for a molecule of ATP or so, or NADPH or something else. And it kind of works like this. You go bump, 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 boom. The chemistry is fairly complex and highly evolved. We start with highly reduced, and then boom, you get down eventually to oxygen. That's this redox tower thing I showed. So here are the two kind of ideas. If you go back to the classic biochemical ideas, people think, well, this probably evolved stepwise. Norm Horowitz at Caltech thought this many years ago. And the idea is that you would have a little bit of energy from some redox jump. You can grab a little molecule of ATP, and then as time moves on, you add a little thing to the end of that chain, and it goes on, and you end up with this highly complex biochemical pathway. Problem here, that little system has to be efficient at the start. If you're going to get, sulfate to sulfite electrochemical reaction, you need very, very precise, highly evolved enzymes to do that. That's not going to be the way life could start. Evolution takes a sloppy system and makes it better. So what I would prefer is to find an environment somewhere in the solar system where you have large gradients, maybe going from oxygen to methane, huge chemical availability, and you can have a sloppy system. Boom. What evolution then will do is take gene systems, duplicate it, tailor it, tinker with it, and you can start extracting more and more energy. So you go from that to this to something like that, and then end up with that system. So, of course, the first time I suggested this, people said, oh, oxidizing conditions destroy prebiotic molecules. Why do you want the origin of life in a place where there's oxygen? Stanley Miller couldn't do it. Harold Urey could not do that with lots of oxygen. But there's a way of doing this. As a geologist, you know that oxygen is sequestered, you get redox stratification. And you can get basins or puddles that interact with oxygens. So I'm going to go to Mars really quick. By the way, this is why I don't like the concept of life in extreme environments, as I said. They moved there. If you do the genetics of something at hydrothermal vents or in high thermal environments, those bugs moved there. They didn't evolve there. Okay? Sorry, NASA, you're spending too much money on life in extreme. Anyway, that's not worth it. Can we find an early environment with large redox gradients? And I think there is one. Let's go to Mars. Here's a view of Olympus Mons. If we go back in time, just today, we know that there's a dichotomy in Mars. The northern basins are very low. The southern highlands are very high and old. We know why it's there. Tharsis is the largest gravity anomaly in the solar system. Basically, when it erupted, the mantle of Mars had stopped convecting, was solid, so the Tharsis province stays there with a huge gravity anomaly. And as you spin around, it has to go on and stay onto the equator. And this is really unusual. the mantle of Mars stopped convecting before the volcanic pile accumulated. It holds up the weight, and it hasn't collapsed in 4.5 billion years. Tells you something. Tharsis volcanoes did not come from the mantle of Mars. They came from a heat source near the core mantle boundary. That's an important point. It means the volcanics equilibrated with nickel-iron metal. The average elevation of Tharsis is also 28 kilometers above the base. That's another critical thing, because that's how you get the oxidants on Mars. Okay, so that's the background on Mars. Two very critical things. Geology and geochemistry, we've known